So as I promised you, 3 quantum numbers. Okay, this is math. Let me denote it by mu, because we are going to conflict with the quantum number n. All right. So 3 quantum numbers n, m, and p, okay, as advertised. So this is a character of 3-dimensional problems. You always need 3 quantum numbers to specify the energy. So now, this is the pillbox problem. So the eigenfunction would, the total eigenfunction would look like C is equal to A times the n-squared Bessel equation, and corresponding to the absolute. Right? And then we have the solution in the z direction. P pi over L z, and then the solution in the phi direction. And actually, I can write plus minus p here because of the symmetry of clockwise and counterclockwise. That makes sense because the rotational energy or the centrifugal area is only determined by the squared of n. So it doesn't matter what the side of n is. Okay. So this concludes our discussion in cylindrical coordinates. Unfortunately, there are no analytical solutions. So let's go into the spherical coordinates, which is actually a simpler problem because of the existence of analytical solutions. So let's consider a similar problem, that of an electron trapped inside of another quantum dot. And this quantum dot is a sphere. So our problem is electron in spherical cavity. So in spherical coordinates, we write down the Schrodinger equation. Again, this amounts to just writing down the Laplacian operator. And the Laplacian operator looks a bit more complicated. It looks like this. And this is the Laplacian operator. All right. And of course, the coordinate system are given by r, theta, and phi. Right? And they form a triplet in the manner r, theta, okay. So phi would be into the page and into the blackboard. That's their triplet. Okay. So now the Schrodinger equation again would be, after rescaling the energy unit, is the minus of the Laplacian times phi of r theta phi is equal to e phi of r theta phi. So I've neglected the potential again. All right. So because we're considering a free electron trapped inside of spherical cavity. Okay. So now we do separation of variables to turn this into 3 eigenvalue problems in the 3 directions. And in fact, if my potential have complete spherical symmetry, meaning that I add in a term here that's a potential that's only dependent on the radius, then the problem is still completely separable because of the spherical symmetry. Okay, but now let's work with this simple problem. So again, I assume phi to be a product of 3 functions. In the radial direction, I'm still going to use r. Okay. In the theta direction, I use the capital theta. Okay. And it looks like this. Okay. Capital theta. This is not some special operation. This is just theta. And then in the phi direction, I have phi again. Okay. So now we go ahead and proceed with the separation of variables by singling out the different eigenvalue problems in the different directions. There's a lot of writing, so it's actually very simple. Alright, so you get the differential operation on R only. This is the first term. Second term, the operator operates only on theta. So we take out the R and the phi. And then this third term is easiest. Okay. We take out R and I forgot to write theta here. R and theta. And then the differential operator operates only on phi. Okay. And this is equal to minus the energy. And I'm going to use K naught squared to denote the energy because we've already rescaled our energy unit. R theta and phi. Alright. So the first eigenvalue problem we identify is again this problem. And this problem is easy, we've already solved this. I just replaced that thing with the eigenvalue let me use a different notation. Let me use M here. But this is convention. So now if I plug this into there, this one is completely multiplicative. This one is not multiplicative. We have differentiation with respect to theta. This one has differentiation with respect to R. So again, we single out the theta direction eigenvalue problem. So let me plug that in. And then after I plug this in, I'm free to cancel the phi, right? So the remaining problem is theta 1 over R squared, plus R times. These two terms, the R and 1 over R squared are all multiplicative, right, on this side. So let me take them out as a common term. And this is multiplying, and then everything left inside is in terms of the theta. And this term, because of the phi eigenvalue here, this term picks up the eigenvalue. So this is m squared, and I turn this into a minus sign. And then this whole thing operates on theta. Okay. So now the natural eigenvalue problem in the theta direction would be just this thing operating on theta. Okay. So let me define another eigenvalue problem, and I'm going to define it a little bit peculiarly. Why? Why the L plus 1? This is with a lot of hindsight. Later when we solve the equation, you'll see that L plus 1 makes L an integer or half integer, so it's convenient. But there is also a strong physical meaning in this plus 1 factor here. Okay. So in the cylindrical coordinate, we extracted that the M, this eigenvalue problem, really captures how much the wave function is rotating in the z direction. So m squared can be a measure. M squared can be a measure of the rotation, the angular momentum squared in the z direction. Now this whole thing here, this is the whole angular part. All the information about the angular part is over here, correct? So this must be encoding the total angular behavior, which is the total angular momentum of the system. Right? And by setting L, well, first of all, the angular momentum in the z direction must be bounded by the total angular momentum. Right? And actually, by writing this plus 1 factor here, we allow for the fact that we cannot know all three components of the angular momentum simultaneously. Because if I didn't have this plus 1 here, then it is possible for m to be equal to L so that all of the angular momentum is around the z-axis, and there are no angular momentum in around the x or y-axis. And that would mean that we simultaneously know to arbitrary precision that Lx and Ly are equal to 0. And that doesn't make sense. And later you'll see that. And the restriction is because Lx and Ly do not commute. When they don't commute, we cannot know their eigenvalues simultaneously. Hence, this +1 actually allows for that uncertainty to be built in. Right. So this is an awful equation. How do we deal with this? So notice that you have sine theta d theta here. You have sine theta squared. So if I make the natural change of variables to do is cosine theta, right? But I know this because I've seen the answer. So maybe it's not natural. So let's make a change of variables. Change this to, again, I'm free to choose the notation. Change this to a function of cosine theta. Okay. Let me make some room. So now, taking the derivative with respect to theta is equal to taking the theta derivative with respect to p cosine theta, right? Yeah. However, no. And then you need to multiply by the, and then from here I can say that this is equal to taking the partial derivative with respect to cosine theta of a function of cosine theta, and then multiply by the partial derivative of cosine theta with respect to theta. So this is just chain rule. And what is this? This is just minus sine theta, right? So now I can go ahead and replace here an operator that operates on the theta eigenfunction with something like this. Okay. So after that, let's work with this term, because this term is purely multiplicative, and the change of variables here is trivial. We just take 1 minus cosine theta. So let's operate on this. Work with this. 1 over theta squared theta d theta sine theta d theta. We replace this with minus sine theta d cosine theta p of cosine theta. Okay? As we have shown over here, this is okay. Right? Everybody is okay with this? An application of the chain rule. Okay. So then it turns into 1 over theta. Let's take this minus sign outside. Okay. Put it here. D theta sine theta squared is just 1 minus cosine theta. Okay. Squared. And then it's d cosine theta p of cosine theta, correct? So now I can think about this as another function of cosine theta, right? So taking its theta derivative is like taking its cosine theta derivative multiplied by minus sine theta, right? So I turn this into multiplying the minus sine theta coming from d cosine theta d theta, right? And then over here we have d cosine theta 1 minus cosine squared theta d cosine theta p cosine theta. Alright. So now let me forget about cosine theta, because now let me just use cosine theta is equal to x. And what is the range of x? Cosine, the theta goes from 0 to pi, right? So x is from minus 1 to 1. Okay. So after this substitution, we find that this big mass of differential operator here, okay, turns into dx 1 minus x squared dx p of x, right? And then let me plug in this term over here. This is minus m squared 1 minus x squared p of x is equal to L plus 1 p of x. Okay. So now if you search online, this is called the associated Legendre function equation. And the solution will be dependent on two integer values, right? The m and the l. So the p l m of x, I'm not going to bother with writing down the general solution. There is a plus-1 solution for it. This is the LM's order associated Legendre polynomial. Later we'll find an easy way to get the expression for these things instead of solving this equation. So anyways, this is the solution. Alright, so the theta direction problem is solved because this has a plus-1 solution. Now let's turn to the radial problem. Are there any questions? No? Okay. Just a change of variable. And actually, if you left it in this form, you can look online and it lists this form as well. So you just copy down the general solution for that. That's also. So now now if we plug in the two eigenvalue problems, the leftover eigenvalue problem for the radial direction is 1 over r squared. Okay, this whole mass over here turns into what? L plus 1. Should be a minus 1. Sorry, definition was wrong. Should be a minus sign here. So this minus the L plus 1, and then this will be divided by r squared. Is equal to. So before you go any further, notice what's the difference between spherical coordinate and cylindrical coordinate. In cylindrical coordinate, when we solved, when we narrowed down the problem in the eigenvalue problem in the radial direction, it was dependent on both the p-value as well. It was dependent on the amount of rotation in the z direction, right? Because the eigenvalue problem was dependent on n, right? Okay. But here, the amount of rotation in the z direction never enters the determination of k naught, which is the total energy, right, by our definition. It never enters the determination of k naught here. And why is that? You can think about it this way. In spherical coordinate, there is really, we choose the z direction arbitrarily by saying that in this direction, theta is equal to 0. But there's actually nothing special about this choice. So how much the wave function revolves around this special axis has nothing to do with the total energy because we are free to choose the z-axis. Right? So it makes sense that m never even enters this determination of the total energy. Okay? It's only dependent on some derivative with respect to the radial equation, and then the total angular momentum. Right? Okay. Does this make sense? What happened? Oh, I need to hurry up. Okay, so remember that comment, alright? So now let's turn to how do we work with this equation. Okay, so once again, we don't have the nice second derivative with respect to r. Okay? We have, these things are plotted together. Okay? But because they're associated, we can work with them. Okay? So let me turn this into this form. Okay, no problem. Okay? And let's evaluate this and this first. Okay? So again, by commutation relation, I can replace this with 1 plus r dr. Right? Taking the derivative across. Okay? And then I replace the other one with dr minus 1. So taking the derivative across in the other way. This way you add a plus 1. This way you add a minus 1. That's just chain rule, right? Okay. So then let's attach the other thing. Which side is just R. Okay. So now let me do another change of variables. And by doing it this way, the change of variables is actually very, very apparent. Okay. So now notice that the R in this bracket is only to the left of the differential operator. So I'm free to take it to the left, right? So I can use it to cancel one here, and I take out 1 over R. Turns into this, right? And then this is strictly on to the right of the differential operator, and I can use associativity to take it here, okay? So dr minus 1 over R. Okay. Now what is this operator? Okay. This operator, let's just do the math. Okay. First of all, you're going to get the second derivative, obviously. And then you're going to get minus 1 over R squared, right? And then you will have a plus, with a plus sign, the 1 over R appearing to the left of the differential operator. And then with a minus sign in the other order, right? So now let me take the differential operator across 1 over R. Okay, let me do this. And by chain rule, this step turns into minus 1 over R dr plus 1 over R squared, correct? Just using chain rule. Okay. So now cancellation happens, and okay, great. This operator is actually just the second derivative with respect to R, but it's operating on a different function now. It's operating on R times R. Okay. So this provides us with a natural change of variables. Minus L plus 1 divided by R squared. Okay, so now still the this thing is bothering us. Let's just multiply by R on both sides. So we get dr squared R minus L plus 1 R squared. Okay, so the natural change of variables is just to scale the radial equation by R, right? So let's say that the eigenfunction is actually U, and the eigenfunction is dependent on the value of L. So we label it as L. UL of R, okay, is equal to R, RL. And then the eigenvalue problem in terms of UL is very simple. Second derivative with respect to UL, and then minus a centrifugal barrier term operating on the UL. This is this. So now again, if I turn this into a Schrodinger equation form, okay, minus sign, plus sign, minus sign. Minus sign because we're looking for bound states, right? Spherical cavity, the bound state. If I take the reference of energy to be infinity, to be 0 at infinity, then it must be a minus. Okay. So now this is again a centrifugal barrier, but now the strength is determined by the total angular momentum. Right. And this is just a second derivative. So this just looks like Schrodinger equation in 1D. Okay. So but then we still don't know how to solve this problem. And again, operator technique. So let me show you how, and it's actually quite fun. So let's turn the sign back.
For L is equal to 0, we have to close 1.
Yeah, for L equals to 0, close 1 is just sine cosine. But we want the sign because we're going to divide by R at the origin, and you don't want cosine dividing by R at the origin, right? So the L equals to 0 closed form is just a sinc function in terms of R, right? Let's think about how we can go from the sinc function and get all of the other equations. Okay. And so this amounts to, I'm going to give you a start here, and you're going to finish it in your homework. Okay, so let's look at this operator here. Certainly I can write it as VR squared minus L over R squared minus L squared over something like this, right? So we have VR, and then we have 1 over R squared. So to do order reduction, we would say that we turn this into a first derivative, and then we turn this into 1 over R. Okay, correct? When we do that, we will separate this. Okay. So L times 1 over R squared. Okay. This is equal to. Remember when we took dr across. Let me show it this way. When we took dr across 1 over r, we had a minus 1 over r squared term left over. This is 1 over minus r squared plus 1 over r. Right? So I can replace the 1 over r squared, okay, minus times an L, which is this term. Right? I can replace it by taking this to this side. Okay? So it's L times dr 1 over r, okay, and then it's minus 1 over r dr. Correct? Okay. Alright, so this turns into dr squared plus, okay, L times dr 1 over r minus 1 over r dr minus L squared over r squared. Right? Okay. So this term obviously comes from plus L over r times minus L over r. Right? And then these terms come from the cross terms, and it's just a matter of determining which one is to the left, which one is to the right. Okay. Notice that the 1 over r with a minus sign appears to the left of the differential operator. Okay. So this factors into dr minus 1 over L over r, okay, dr plus L over r. Okay. So we have successfully reduced the order. In a way. Okay. And then what's even more interesting is by thinking about how these operators commute. Okay. You can construct actually all of the eigenfunctions just starting from the sink. Oh, sorry. And I'll let you complete this operator technique in the homework. So now we move on. We move on to the second part. Okay. So the second part, we're going to think about rotations. Okay. And what are the generators of rotation? So physically, what does angular momentum do? What does linear momentum do?
You can give us a break there.
Oh, okay, yeah. Give you a minute. All right, so let's have a 5-minute break.